Welcome to my YouTube channel. Today we will see example 2 mixing chamber. Previously we have seen mixing chamber example where we have the vertical inlet. This time I have changed the geometry. Now in example 2 we have two inlet in inclined position at 45 degree. Both inlet have same diameter and we have one bigger diameter, that is the inlet 1, also the outlet and wall. Boundary condition is given, density is same, viscosity, conductivity and specific heat is given. For inlet 1, boundary condition is 1, velocity is 1.2 meter per second, temperature is given 20 degree, intensity is 5%. Inlet 2 and 3 we have same velocity 2.5 meter per second, temperature is 40 degrees Celsius and intensity is 5 degree. Reynolds number is given, and based on that we have to find out the flow is laminar or turbulent, and based on that we will choose the model for the post processing. So we will start with the ANSYS Fluent. First we will call the geometry. I have created geometry in Creo, and we will import that geometry. Double click or edit, right click and edit in design modular. Design modular is starting, it will take time. I have created two more video on the same mixing chamber, but the orientation of the mixing chamber is different. This is because we have to observe, or we have to see what is the effect on the flow field if we change the orientation of the mixing chamber. Yeah, now it is open. Just say generate. Yes, go to the view and of the frozen body, make parallel to the screen. Yes, now you can see we have one part body, that is a mixing pipe. This is our domain, and now the first step is to create the inlet and to define the inlet, outlet and wall and symmetricity. Again it is the half portion of the model because of the symmetricity. If you have such kind of problem, you have to model a half portion only to save the time and all the efforts. So right click and say name selections. Here the inlet 1, say generate. Inlet 2, inlet 3, generate. Then we have the outlet, generate. Then symmetric plane is there. Okay, now last is wall, so we'll select rest of the body and we'll say wall, generate. So we have defined the inlet, outlet and symmetry. Save the model. I will save on my local drive. next step is meshing. So we'll attach mesh, double click on mesh. Meshing is starting. Yes. Now you can see we have the name selection, and in the geometry we have the domain mixing pipe. In the mesh we will change the mechanical to CFD, and in the sizing we will change the option size function, that is the proximity and curvature. We will take a fine mesh, then transition should be slow, and we will keep the rest of the option as it is default, and just right click on mesh and say generate mesh. Now our mesh is done. Now you can zoom in or zoom out to see the meshing at a small inlet or overall structure. You can also check the mesh quality. Go to the quality and take the mesh matrix like orthogonal quality. First we have to check. So as I mentioned earlier that orthogonal quality should be close to 1, and below 0.5 we have to rectify that elements, and the same thing you can check. Now you can see we have the minimum mesh element size is 0.34 and maximum is 1. In same way you can check the skewness, and also you can check the aspect ratio. So number of element we have 1 2 4 3 3 total numbers. Yeah, so this is from the meshing side. We'll start with the pre-processing. Before that, save the project. Then attach Fluent setup to the mesh. If you do like this, you have to always update the mesh. Yeah, now mesh is updated. Now we will go to the, we will click on setup, double click. Yes, again our problem is three-dimensional. We will take a double precision options and we will say OK. Yes, in the console you can see the zone and wall, symmetry, outlet, inlet, mixing pipe. You will get all this detail here. Also the tetrahedral cells for particular zone, they are defined here. Okay, first step, we have to change the unit. We will change the unit of temperature, then we'll close it. Here you can also check the report quality. Now you can see orthogonal quality, minimum orthogonal quality is minus 0.2. We will use the pressure base, not a density base. In the model, as I mentioned, first we have to on the energy equation, then our flow is not a laminar based on the Reynolds number, it should be a turbulent. So we'll use the K epsilon model and we'll keep the rest of the option as it is. So we have set the model, then we'll go to the material, we'll add material water in Fluent database, select any and type W, water liquid, yes. Now copy and close. Here you can change the property as per your boundary conditions mentioned in the problem descriptions. So this is the specific heat. Specific heat is given 4216, and this is the 0.67. Viscosity is given 0.8 and change it and close it. In the cell zone, you have to confirm that is the mixing pipe. This is your domain and it is for fluid, not a solid. In the boundary conditions, we have the inlet, outlet, symmetry and wall. Then we will go one by one. First we will take the velocity inlet, because in the problem descriptions they have given a velocity, so that's why we have choose the velocity inlet. Otherwise, if they have provided mass flow rate, then we choose the mass flow inlet. So it depends on the boundary conditions. So here I have selected a velocity inlet, just edit 1.2, I think. Yes, for the inlet 1 it is 1.2 meter per second. Turbulent intensity is 5%. Go to the thermal and here we have the temperature 20 degrees Celsius. Say OK, then go to the inlet. Again it is a velocity inlet and it is given 2.5, and the thermal temperature is given 40 degrees Celsius. You can copy also. If your boundary condition is same, you can copy and here it will ask from boundary zone. So you can say from boundary zone inlet 2 to boundary zone inlet 3, copy. So copy inlet boundary condition to all selected zone. Okay, and now you can see in the inlet, edit it. Now all the values will come automatically, 2.5 and the 40s. Yes, then the outlet is our pressure outlet, and obviously we will keep default as it is in gauge pressures. Here we can put a default 26. For the symmetry, it is symmetry, and wall we have to edit. It is a stationary wall, not a moving, so we'll keep a stationary. Thermal body temperature is not given, so we will not mention anything here. Otherwise, we have the option heat flux or temperature that you have to define. So from boundary condition side, we have done. We'll go to the reference value. Here you can, in drop down menu, you can choose where to start from the inlet 1, and all the property from inlet 1, it will come here, all the values. Now you can see the velocity 1.2. In the method, yes, last time we have seen the simple, this time we will go for the coupled. The difference is that in the coupled, the conversion time will be reduced, and the rest of the option is the same. Always take the least square cell base. Pressure is second order, momentum is second order, upwind, and rest of the thing is the first order. Again, we have to set the monitors, that we will see later on. In the initializations, we will go for the hybrid. We will say initialize. So here in the console you can see the hybrid initializing is done, and run the calculations. Number of iterations, again we will use 150, and we will check at what iteration it converge, and we will say calculate. Regarding the residuals, we have kept the default value, that is 10 raised to 1 minus 1. Now you can see in the convergence, it is going down below the 10 raised to 3, and after that it will be settled down, and energy equations is 10 raised to minus 4, and it will go 10 raised to 6. So once it is done, it will not change later on, so it means that it is converge properly. And you can also check the flux imbalance. These two things will confirm that your problem is converge or not. Yes, calculation is done. Okay, then we'll go to the post processing in the result box, graphics, but before that we will set the surface monitor. We'll take a ISO surface, and here we'll take a mesh for the outlet and for the Z directions, and here we will say Z outlet, and we will compute. So it will compute, and we will close it, and in the plot, in the XY plot, new, here you have to keep x1, and we will see the temperature and static temperature at 36 the monitor. Okay. Okay, we'll see this later. First we will see the contour. Here we will check the velocity contour, so we'll change the name velocity. Take the first four options and select the velocity and velocity magnitude at symmetry plane with the smooth options, say display, and make it parallel to screen. Go to the viewing and opt the lighting options so your model will be clear. Now you can see we have given inlet velocity at larger inlet, that was 1.2, and for the small two inlets we have given 2.5, and now you can see the flow distributions. In same manner we can see the pressure distributions, so we'll go for pressure with the field options. Take the pressure and static pressure at symmetric plane. Yes, now here you can see we have the little bit pressure drop in this region. Okay, and this green also because of sharp edges. If we do some fillet here, maybe pressure loss will be reduced. Also we can see the new temperature contour and take a temperature, static temperature field at symmetric 1 display. Yes, as we define temperature at inlet boundary, that is the 20 degree, so you can see here 20 degree and here as a 40. So this is the temperature distributions. So only this area we have the temperature, and later on it is reduced to the almost 32 or 30, and one side of the outlet you can see there is a temperature drop completely. Regarding surface monitor, we have created a surface monitor. Yes, Z coordinates, create it again, and you have to confirm that it should be in the list actually, and then go to the plot, and new, and here you can go to the temperature and static temperature and select the Z and plot it. Now you can see this is the static temperature versus positions. Yeah, so in this example we have seen the flow field. If the geometry orientation is changed, and what is the effect of that geometry change on the flow field. If you like my video, please like and subscribe my channel, and in next example we will see the different orientation of the mixing chamber, and we will again see the flow field. Yeah, thank you very much.